In this video, we'll be looking at the final part of the particles section in this booklet on conservation laws. Now, conservation laws are the use and application of the quantum properties that we've covered recently. So we know that energy is universally conserved in all situations. Momentum also falls into that bracket. As a result, neither of those can ever be given as a property. They will always be stated in the question. And remember, mass is just the same as energy through E equals mc squared. So charge, the only property that previously would have been a conservation discussion. But now we have baryon numbers and lepton numbers as well. Now these are always conserved regardless of what else is going on. And in the weak interaction in particular, they are always shown to be conserved in an equation. Now, strangeness is different. It will change in a weak interaction. So it's assumed that it will decay. Any strange quark will turn into a down quark, for example. But under the strong interaction, strangeness is conserved. And that is the only time that that is true. So if strangeness is conserved in an equation, then you know that must be representing a strong interaction. Now looking at this example, we have beta plus decay, which as we know is a weak interaction. What I would normally do is below the equation, I would have rows Q, B, and L, where I can represent the values for the charge numbers, baryon numbers, and lepton numbers for each particle above. So following this through, the charge of a proton is 1, which then becomes no charge from the neutron, plus 1 from the positron, and 0 from the neutrino. So it's conserved, 1 on each side. Similarly, we could do the same for the baryon number and the lepton number. Again, just be careful with leptons. Antiparticles are -1 regardless of what the charge of the particle is. So all we're doing is balancing equations, making sure the left-hand side matches the right-hand side. This can also be used as a means of determining what a missing particle must be. So, for example, if we wanted to find what the neutrino space was on this equation, if we hadn't seen the equation before, we could do so. So let's test this out. So for beta minus decay, we're going to do this traditionally. For the electron capture, we'll imagine that we don't know what one of the particles is and see if we can identify it. So for beta minus decay, we have a neutron becoming a proton and releasing an electron and an anti-electron neutrino. So conserving, we need to check charge, baryon number, and lepton number. Sometimes they'll only ask you for 2 of these, but there's no harm in showing 3 correctly. So for charge, we go from 0 to 1, -1, and 0. Conserve. Baryon number, the only baryons are the protons and neutrons, 1 on each side, it's conserved. Lepton number, again the baryons are obviously not leptons, the electron is, and an antineutrino is an antilepton, so again, balanced. This is proof that this interaction is real and can happen. So if you were given an unknown equation, you might have to check its viability through this process. Now for electron capture, let's say you're given that a proton plus electron turns into a neutron and instead of what we know as a neutrino, an unknown particle. So how can we figure out what this particle must be? So if again we conserve charge, baryon, and lepton numbers, we can determine key features about it. So the proton and electron charges cancel out on the left-hand side, meaning both particles on the right must be 0. So we now know it has no charge. Baryon numbers, the proton and neutron are both baryons, so this unknown particle can't be a baryon. So at this point, it's a neutral, meson or lepton. So let's check the lepton numbers. That'll finish it off. So the electron is the only lepton on the left-hand side, whereas the right-hand side must have a lepton to balance it. So we now know that this particle has no charge, is not a baryon, is a lepton, and the only particle that matches is a neutrino. And to finish it off, as we have an electron present, this must be an electron neutrino. Simple as that. Thank you for your time.